Hello everyone, and welcome to today's episode. It is I, ichino-ani, your favorite podcast host. Today is Monday, August 3rd, 2026. I'm so excited to talk to you today, because we have a super fun and mind-bending topic to explore together. Are you ready to learn something amazing? We are looking at an incredible new paper from the archive. The title is Learning to Trace Seiberg Dualities, and the URL is arxib.org/abs/2607.28628v1. It is a very long link, but the ideas inside are absolutely magical, and I am going to explain them all to you. So, what is the big problem this paper is trying to solve? Imagine you have a giant box of building blocks. You build a massive, complicated castle. Then, your friend comes over and builds a completely different looking castle. But, what if I told you? But both castles are actually the exact same toy, just arranged in a secret, special way. In physics, scientists call this a duality. Dualities are special rules that show how two completely different physical systems are actually exactly the same on the inside. Specifically, this paper talks about Seiberg dualities. This involves things called quiver gauge theories. You can think of a quiver as a treasure map of dots and arrows, where the dots are groups of particles, and the arrows show how they interact with each other. Now, the rules to change one quiver into another are well known to physicists. We call these step-by-step changes mutations. But here's the big problem. If I give you two giant quivers, how do you know if they are dual to each other? How many mutations does it take to turn the first one into the second one? You just guess. Number of possible paths grows so incredibly fast that even the biggest computers in the entire world get completely stuck. It's like trying to untie a massive, tangled knot while you are blindfolded. To fix this enormous problem, our researchers decided to use machine learning. They built super smart artificial intelligence programs called graph neural networks. They created two very special tools for this job. The first one is called the distance graph neural network. Let us call it the akin for short. The DAN looks at two different quivers and guesses exactly how many steps it will take to turn the first one into the second one. It's like looking at a confusing maze and guessing exactly how many footsteps it will take to get to the cheese. The second tool is called the advisor graph neural network. We will call this one the akin. The akin is like a helpful little guide whispering in your ear. Looks at the quiver you have right now, and it points out which dot you should mutate first. It gives a probability, saying this dot is the absolute best choice to get closer to the final goal. Now, how does this amazing new AI compare to older technologies? Before this paper, computers used something called breadth-first search. That means the computer blindly tries every single possible move, one by one, step by step. But there are 10 possible moves on the first step. It tries all 10. Then, for each of those 10, it tries 10 more, that is 100 moves, then 1,000, then 10,000. It gets too big and too slow. But with our new neural networks, AI acts like a smart GPS navigation system. The researchers combine the akin and the akin to make a powerful hybrid pathfinder. Instead of exploring every silly path, the akin says, hey, ignore those bad paths, only go this way. And the DAN says, yes, I can see the goal getting much closer. This makes finding the answer incredibly fast and highly accurate. They even compared it to a method human physicists use, called the lowest common ancestor pathfinder. You try to shrink both quivers down to a simpler shared shape. The AI hybrid pathfinder proves to be much more efficient, especially as the problems got larger and more complex. Now, you might be wondering, why do we care about quantum physics and quivers? How does this apply to our everyday life? Well, the math used to solve this problem is actually everywhere around us. Let me give you 3 specific application examples based on the concepts in this paper. First, think about city traffic and smart navigation. Right now, and you use a map app on your phone. It looks at the shortest distance, yet in a real city, roads close. Accidents happen, and the rules changed instantly. This is just like mutating a quiver. The hybrid pathfinder technology could be used to route millions of cars at once. By treating intersections as dots and predicting the absolute best global mutations for traffic lights, you would look at the whole city and untangle traffic jams before they even happen. Second, let us talk about medicine and drug discovery. When scientists invent new medicines, they have to test thousands of molecular structures. Molecules are just graphs of atoms connected by bonds. very much like our physics savers. Using a system like the advisor graph neural network, computers could look at a sick cell and look at a healthy cell and predict the exact sequence of chemical mutations needed to transform a sick state into a healthy state. This would save the nerves of blind guessing in the laboratory, because the AI would act like a brilliant guide, pointing right to the cure. Third, we have supply chains and global shipping. Imagine a huge company that ships millions of packages every single day. The network of warehouses, trucks, and airplanes is a giant, complicated graph. Sometimes, a giant storm stops an airplane or a delivery truck breaks down. The company has to completely mutate the shipping routes, keep things moving. By using the distance graph neural network approach, the company could instantly calculate the true cost of reorganizing your entire network. The AI would seamlessly trace the optimal path through the chaos, ensuring your packages arrive on time without wasting fuel or money. Let us dive a little deeper into how the scientists actually built this marvel. The researchers had to generate a massive training data set to teach the AI. They started with simple seed theories, which come from beautiful geometric shapes in string theory. Then, they applied the mutations over and over again, up to 12 times, to create a massive family tree of theories. Once they had this huge map of how theories connect, they trained their graph transformers. A graph transformer is a special AI that does not just look at one tiny dot. It looks at the entire picture all at once. This is called a global attention mechanism. The John learns the global differences between two quivers, while an akin learns the local rules of what makes a good first step. When they put it all together into the hybrid pathfinder, they found it had a 100% success rate on their test data. 100%. That is like getting a perfect score on the hardest math test in the universe. Even when they tested the AI on outer distribution theories, which means puzzles the AI had never ever seen before, it still performed incredibly well. It learned the hidden rules of the universe, rather than just memorizing the answers. They also tested the breaking point of the AI, to see when it would finally get confused, and they found it holds up strongly, even beyond its training limits. This paper is a massive leap forward for science. It proves that artificial intelligence can serve as a powerful tool for theoretical physicists. It acts as a magical oracle, helping humans navigate spaces that are just too mathematically complex to explore by hand. It is not just about solving abstract math. It is about building tools that learn how to untangle complex systems. Whether it is quantum physics, traffic jams, or curing tricky diseases, learning how to find the optimal path through chaos is one of the most important tasks for the future of technology. I hope you all learned something truly amazing today. It is so much fun to explore the cutting edge of science with all of you. Keep exploring your world. Keep asking brilliant questions. And never ever stop learning about the magic of science. Thank you for listening, and I will see you next time.